So, Dr. Mack,
yes.
Today we are going to learn about, and I like this phrase, cosmic noon.
Cosmic noon.
That involves us, right? Like that involves the creation of this one, the Milky Way.
Yeah.
Ours.
Yeah, it involves the creation of most of the stuff like that we see.
Great.
Yeah, yeah.
Okay, so as I just mentioned, in this conversation, we're going to talk about cosmic noon. Cosmic noon is interesting because, one, we are nearing the point in our journey through the entire history of the universe where, like, we exist. And also, two, it involves the mystery of what I'm calling a secret cosmic wind that has caused the accelerated expansion of the universe, something that Albert Einstein may have recognized unknowingly. So we'll talk about that mystery, and we'll even discuss a theory for how our solar system came to be. We'll explore the ways cosmologists have posed and attempted to answer big questions about our origins on a grand scale. But first, we need to talk about where we are in our timeline, and also what time even is. So here's our conversation.
So let's kind of go back, because we did a few departures from the timeline because we were talking about the cool, weird stuff with dark matter and black holes. So we got to the Epoch of Reionization. We went through the Dark Ages, Cosmic Dawn, Epoch of Reionization. And Epoch of Reionization is when the stars just turn on enough to ionize the intergalactic medium, to take all of the neutral hydrogen gas out there and split it into ionized hydrogen. So protons, electrons no longer connected, right? That's ionized hydrogen. And so from that point on, most of the gas in the universe, most of the intergalactic medium is ionized gas, just very low density ionized gas. And that allows the universe to be transparent to visible light. So that means starlight can flow through the universe unimpeded by the gas, right? That's the period that we're in now still. Like the universe is mostly ionized gas and the starlight can go through. But over time, like the process of the formation of galaxies and the formation of stars has kind of varied as stuff comes together, right? So the matter comes together via gravity, and you get these clouds of gas, and those clouds of gas form stars, and, you know, they're in galaxies, and it's just bigger clouds of gas that often sort of form into disks. And then you get star formation in the disks of these galaxies, and all that stuff is kind of condensing and swirling around, and galaxies are like being attracted to each other with their mutual gravity and sometimes colliding with each other. And there's this constant sort of churning and colliding of stuff in the universe. And when that stuff comes together, you get the formation of new stars and galaxies and so on. And that process just kind of keeps going on. But there's a sort of balancing thing that happens between, like, the gravity is pulling everything together on, you know, galaxy scales, galaxy cluster scales. Things are kind of slowly condensing over time, but the universe on the whole is getting bigger, right? So the space between galaxies is on average getting larger. And so there's a kind of a balance where in the real early universe, there hasn't been enough time for all of the gas to condense for a lot of the galaxies to form, because it takes some time for everything to gather together. But if you wait too long, then the galaxies are being pulled apart from each other on large scales. And so you don't have as much sort of structure formation if the universe is too big and there's, like, you know, there's too much space in between everything. This kind of sweet spot is somewhere around 2 to 4 billion years after the beginning. So kind of in the universe's adolescence, maybe, is when there's, you know, there's a lot of stuff coming together and the expansion of the universe has not pulled too much stuff apart.
Right. Okay. That makes sense. It's a bummer to hear that we're not still in the sweet spot. I was hoping to be amid the sweet spot.
Yeah.
But we're not.
Yeah. So that time period, which we call cosmic noon.
Great phrase.
Yeah, it's good. I always feel like I hear the phrase cosmic noon and it conjures up this image of some kind of like Wild West ranch. Like, I don't know, somehow the idea of like it's a hot day in the West, and anyway.
Right. Yeah. Cosmic noon would not be a bad name for a sort of psychedelic rock band.
That's true. Yeah.
It also wouldn't be a bad name for an artist residency. You know, like have you applied to Yaddo and Cosmic Noon?
Yeah.
So I like that. By the way, Katie, there are times when you are talking to me, and this was just one of them, where you're describing this sweet spot between, you know, the gravity of all this stuff being pulled together and the universe itself expanding. People are always like, oh, you don't know that the Earth is moving. Well, I do when you talk like that. I suddenly feel it. I'm going 25,000 miles an hour and I'm spinning on a rock that's spinning around a rock that's spinning around a freaking black hole at the center of the galaxy. I'm feeling it right now. I'm feeling it pretty intensely.
Yeah. There are all these like just huge forces out there, you know, and they're altering how the universe works. They're altering what the universe is made of, like all the dynamics of everything. And we're part of that, you know, like we're just sitting there. We're just part of that.
Yeah. We're like little protons on the tide of empire.
Yes.
Oh, boy. Okay. So 2 to 4 billion years ago, we've got this cosmic noon.
Yeah. And so a few things are kind of happening more than at any other time in the universe. And I should say that the way we know about this time period is through like directly looking at it, which I've said this a few times that we learn about the past in the universe just by looking at it. And it sounds very simplistic, but it's absolutely what we're doing. And I still find it kind of wild because, you know, if you talk to like an archaeologist or paleontologist or something, they're looking at like remnants, they're piecing together a timeline from debris, from, you know, remains, like all this kind of stuff. Like, you know, you have to kind of put all the clues together and figure it out. Like we can just look at the past. We can just directly see it.
Yeah, because of the gift of light.
Yeah.
It's amazing.
Yeah, it's wild. We can look at galaxies at different times in the past. And at this point, I'm going to have to talk about Redshift again, because as a cosmologist, this is how I think about the timeline. And I will get too confused if I try and do it another way. So we talked about Redshift a few times. Redshift is a term for how the expansion of the universe is stretching out the light as it's traveling to us from distant objects. You could also have redshift from something moving away from you, either moving away from you or the universe expanding the light. It's kind of an equivalent looking thing. The light gets stretched out. And so things that would be shining in ultraviolet or visible light might be shining in instead visible and infrared light, because the light is sort of stretched to the redder or longer wavelength part of the spectrum. And if you look at different epochs of the universe, because the universe has been expanding, all of the galaxies at a certain time will be redshifted by the same amount, right? And so we can label time periods by the redshift, by the degree to which the light has been stretched out.
So 2 billion years ago might be, another way of saying that might be redshift 6 or something.
Yeah, so 2 billion years ago is not that high redshift, but okay. Yeah, like so,
but
like
no.
But
do
like,
you genuinely say like redshift and then a number?
Yeah, exactly. Yes.
So I was making a joke, but it turns out that you actually do say redshift and then a number to represent what I would think of as billions of years.
Yes. Yeah, and it's connected to the size of the universe at that time, also.
Right.
So I think I mentioned this before, but there's this concept of the scale factor, which is like, if you take the scale factor to be like, for example, like something related to the average distance between galaxies at a particular epoch, then, you know, at another epoch, that scale might be twice as big. And so we use a number called the scale factor, which we write down as A, and we define the scale factor to be 1 today. So whatever that distance is, it's 1 now. And at previous times in the universe, it was maybe like half of that or a third of that or whatever. And the redshift is related to the scale factor in an inverse way. So A equals 1 over 1 plus Z, where Z is the redshift. So today is redshift 0. So the light coming from today is not redshifted at all.
Mm-hmm.
And so the scale factor today is 1 over 1 plus 0, which is 1.
Okay.
So at redshift 1, the scale factor is 1/2. Because it's 1 over 1 plus 1. And so that means the universe was half as big at redshift 1.
Got it.
And it turns out that Redshift 1 was when the universe was about 6 billion years old. So it's about 13.8 now. So, you can kind of count back.
Okay.
Redshift 2 is when the universe was a third as big as it is now. And the universe was about 3 billion years at that time. Redshift 3, the universe was a quarter as big as it is now. And that was when the universe was about 2 billion years old. And then you can go all the way to like Redshift 10. The universe was 1/11th as big as it is now. And the age of the universe was about 500 million years old, so about 500 million years old.
Okay.
So the reason we think of these epochs in terms of redshift is because the redshift is directly observable. We can look at a galaxy and we can see that all of the absorption lines that should be at certain frequencies are shifted as a block to different frequencies. And so we can see what that shift is. And so we know exactly how much the universe has stretched out since the time the light left that galaxy. And that's a monotonic function, right? So it means that, like, if the thing is older, the redshift is going to be higher. The thing is farther away. Like, it's always going to be in that direction.
Right. And so when you look at a distant galaxy, you can tell how far away it is, approximately. You can tell how old it is, and how far away it is and how old it is are always going to be related.
They're related. Now, the physical distance, that gets real complicated real fast.
I'm sorry. I apologize for bringing up physical distance.
Don't apologize.
I'm always trying to understand this stuff as if I were like looking out my window at the universe, and I need to understand it a little differently, I think.
Well, yeah. No, the reason physical distance is a problem is because in an expanding universe, you can never just like lay down your measuring tape and see how far the thing is. Because, like, are you asking how far away it is now? Are you asking how far away it was when the light left it and it has since moved? How are you measuring how far away it is? Is it via how much the light has spread out? Which is one way you can kind of figure out distance, by this inverse square law of the light spreading out. Is it by how big it looks to you, like the angular size in the sky? Because that also changes as it gets farther away, right? But not in a normal way, because if it's a long enough time ago, it was so close to you that it made a big picture in the sky and then it moved away. And so that's not reliable as in terms of like how far away is it now, it's because that's not a monotonic function that changes. So there's a famous paper called Distance Measures in Cosmology by a guy named David Hogg, and it's like a staple of graduate students everywhere because it goes through all of the different distance measures and how they're related to each other and how you can calculate them with the redshift given a certain cosmological model. It's just deeply confusing because all of these things, they're all different ways of measuring the distance because there's just no objective distance in an expanding universe. And so you have to calculate it via, what you actually see in terms of the redshift and like the brightness or the angular size or whatever, and then a model of cosmology where you're modeling out how the universe has changed since the light left that object.
I don't want to go off on too much of a tangent, but I mean, what even is time then?
I mean, right? Right? I mean, because time also changes based on what you're doing and where you are and how you're moving. So time is not objective either, right? We talk about the look back time when we're talking about distant objects, which is like how long ago the light left that thing. But that's modeled based on our model of how the universe has been evolving because we don't know that objectively just by looking at the object. We have to look at the redshift. The redshift is the thing that we know the best because we can just see that in the spectrum, and that's very precise. It can be done very precisely. So we know the redshift, but the rest of it is all modeling based on how we think the universe has evolved since the light left that object.
So we really shouldn't even be talking about how many billions of years ago it was because it's a little bit like transferring a redshift, which is something we can directly observe, to a model of time that is maybe not, oh God.
Yeah, I mean, we have a pretty good model of, the expansion history of the universe. Like what the model contains is there's an equation that contains like how much dark matter there is, how much regular matter there is, how much dark energy there is, how much radiation there is, whether the universe is overall flat or curved in its geometry, which we talked about at some point about like.
But we need to know all of that to know if time is real?
No. We need to know all of that to know the age.
Yeah, okay.
To derive the age of the universe. That all goes into the model.
Okay.
And it should be pretty straightforward because we know a lot of those numbers very precisely. The one reason why it's not super straightforward at the moment is because one of the numbers that goes into that is the current expansion rate of the universe. And right now, there's kind of this problem where, depending on how you measure the current expansion of the rate of the universe, you get different answers. And this is called the Hubble tension. So the number is called the Hubble constant or the Hubble parameter.
Good phrase.
That's the current expansion rate of the universe. Yeah, and whether you measure that by looking at distant supernovae and how the expansion rate seems to have changed based on the supernova redshifting and the distance changing, or if you look at it by looking at the cosmic microwave background and the patterns in that and then derive something from the model of the universe, you get different answers. And there are several other ways to measure it that all give answers that are somehow, in the range between these two. Some are closer to one, some are closer to the other. We don't know the resolution to that problem yet. And so there's a difference. And so we don't know exactly which number to put into these equations to get that age exactly right. And so, if the supernova people are right, then the universe is actually less than 13.8 billion years old. If the cosmic microwave background people are right, it's about 13.8 billion years old. I use 13.8 because that's the number that's been most popular since I've been doing cosmology, but it could be a little less than that if the supernova people are right. Like, we don't know for certain exactly what that number is, and we haven't figured out why those two measurements disagree with each other.
I'm feeling anxious again. Just full disclosure. It's not your fault. It's the universe's fault for having a Hubble tension.
Right.
And also because suddenly I don't know what time is. But I like the phrase Hubble tension a lot. I feel like that would also be a good, maybe not a good band name, but a great first album name.
Right. Yeah. That's true. Yeah.
So it's got that going for it.
Yeah.
All right. Okay, now that I'm anxious, it's cosmic noon.
Right, yeah. So that whole tangent is why I got uncomfortable when you asked about exactly what age, what time we're talking about, because I think of this all in terms of redshift. So
I'll never make that mistake again.
No, it's fine.
I will never ask you for how many years ago something was. I'm very sorry.
It's fine.
Because there are no years. There is no time. Everything is contingent upon everything else. So, huge error by me.
There is time.
There is time. Okay.
we just have really complicated clocks that we don't understand. That's all.
Okay. Great. Okay, there are a few key things here that are worth re-emphasizing. As the universe expands, distant objects move further away from us. As this happens, the wavelengths of light traveling to us from those objects get stretched out, which is called redshift, and it can offer us information about the expansion of the universe. So while figuring out our physical distance from something is much more complicated than I first assumed, and time, it turns out, is even more complicated, redshift allows cosmologists to measure how far away things are from us, which can help us figure out things like how old the universe is. But there's a twist: the Hubble tension. There are a few ways you can calculate the expansion rate of the universe. One is by observing the redshift of distant supernovae. Another is by analyzing the radiation that emanated not long after the Big Bang, known as the cosmic microwave background. And each option leads to a different number, a different age of the universe, which is an uncertainty that can be difficult to sit with.
Okay, so cosmic noon was around redshift 2 to 3.
Okay.
And I think that's around 2 to 3 billion years in terms of the age of the universe. It happens to be kind of in the same vicinity. So, around that time. So cosmic noon is defined as when star formation was at its peak. Okay, so there's a couple things that go into that. One is just, one of the best ways to form a whole lot of stars all at once is to take two galaxies that have a lot of gas in them and slam them together. And when you do that, all the gas in the galaxies like comes together, you get these shock waves, you create these little like nodules of high density gas, and stars can form very quickly in those environments. And many, many years ago, around Redshift 1 to 2, so, somewhere around like 3 to 6 billion years of age of the universe, somewhere in that sort of range, around 5 billion years, let's say. That was when galaxies were merging most often. And it makes sense that there would be a time when that was happening the most often because, galaxies kind of form and then the gravity pulls them together and it takes a little time for that to happen. But if you wait too long, then the universe is expanded so much that they're not coming together as often, right? And so there was that peak of galaxy merging, like galaxy merger processes. And then there was a peak of like stars forming, and it was kind of all in the same vicinity where you get a whole bunch of galaxies colliding a lot, you get stars forming a lot, and there was just this burst of like most of the star formation was happening like around that time.
And is that when our galaxy came into being?
Yeah, so our galaxy started to come together in sort of the first billion-ish years of the universe. Some of the matter started to come together. But the cool thing about our galaxy, I mean, most large galaxies, is that process of like gravity pulling things together, it doesn't just pull together like pristine clouds of gas. It also pulls together like things that have already formed their own galaxies. And so a large galaxy like ours will have eaten lots of little galaxies over its lifetime. So there will be some little dwarf galaxy. It formed very happily on its own. It had its own gas cloud. It formed its own little stars, but it was caught in the gravitational field of our galaxy and, kind of was swallowed up by it. And our galaxy has swallowed up like, I don't know, probably dozens of little like galaxies in their own right over the years, over the billions of years it's been around. So I think there's something like, I think we know of at least 5 of these episodes of our galaxy swallowing up a smaller galaxy. And the way that we see it, the way that we know that this has happened is we can see like streams of stars in the halo of the galaxy. So the galaxy is like there's the disk and then there's the halo, which is the kind of like spherical region in which our galaxy lives. And the dark matter is spread throughout the halo. But also in the halo, there are globular clusters, which are these little clumps of very old stars, and some of those came in from other things as well. But there are these streams of stars that we can see like stretching across the night sky. And you can find these cool images, these visualizations of these streams of stars where they color code the stars that belong to the same stream. And the way that you figure out which stars belong to the same stream, I mean, they're not like a very clear line necessarily. But if you look at the chemical abundances of the stars and stuff, you can kind of figure out which ones formed around the same time. And so you see a whole bunch of stars that formed right around the same time, and they're all in kind of an arc across the sky. And that's an indication that they came from a galaxy that was pulled in and kind of like spaghettified, kind of like pulled apart, stretched apart by being, sort of flung around inside the gravity of our galaxy as it's like orbiting and stretching out. And so there are all these stellar streams, and you can do amazing things with these streams. You can do what's called galactic archaeology. This is a subfield in cosmology, galactic archaeology, where they are trying to figure out the history of the galaxy by looking at these streams and the sort of chemical abundances of stars spread throughout the halo of the galaxy to see where all these things formed, when they formed, and how they came into the Milky Way. And it's a fascinating field.
That's so cool.
Yeah. Another term for that kind of stuff is near-field cosmology. So cosmology is usually you're looking at really distant objects because you're looking at the past. But near-field cosmology is you're looking just inside the Milky Way and doing cosmology by learning about the distant past of the universe by things that fell in to our galaxy and got swallowed up.
That's beautiful.
It is. It's a wonderful tool we have, and we have a really good set of observations now that we can use. So there's a satellite called the Gaia satellite. It's a European Space Agency mission, and it's just charting the stars in our galaxy. It's making this amazing 3-dimensional map of the Milky Way, trying to get a census of like a billion stars, and not just get like pictures of where they are, but very precise locations and motions of the stars, like three-dimensional motions of the stars, to really map out how the stars in the Milky Way are moving. And that mission has given us so many of these stellar streams and helped us to figure out like how things have come into the Milky Way, what kinds of events might have triggered, star formation and things like that in the past. It's telling us about the shape of the galaxy. So our galaxy is not completely flat. There's like a warp to it. Though to the disk of the galaxy that's a little bit warped. And so we're learning about how like a galaxy collision might have like warped the Milky Way disk. Like all kinds of stuff like that you can get by really, really precisely mapping all of the stars in our galaxy. And that's one of the things that the Gaia satellite is doing. So it's helping us to learn like where we specifically came from. I mean, there's even a story, like a new study that suggests based on Gaia data that like a collision of a galaxy into ours might have triggered the formation of the solar system.
Our solar system?
Yeah.
Oh, so like we really did come from maybe that from a collision.
Like from the collision might have like increased the amount of star formation at that time in a way that could have helped create the solar system. Yeah.
Wow.
Yeah, it's wild what you can learn by just mapping out where all the stars are, how they're moving, what their elemental abundances are, and like piecing together. And this is why it's called galactic archaeology, because you're really trying to use these remnants and these clues, like chemical clues and stuff. So this is where you can't just look at the past now. You have to actually do the clue gathering because we're trying to do something nearby, because we can only look at the past far away. We can't look at the past nearby.
Right.
But with these kinds of studies, we can try and learn stuff about like where we came from, which is very, very cool.
Yeah. It is astonishing to me to think about the relationship between, all this star formation and our star, and how our star was the end-all, be-all of our understanding of cosmology for the vast majority of human history.
Yeah.
And how what a leap it would be to try to understand the twinkling stars at night as in any way similar to our star.
Yeah, it's kind of amazing. I mean, I was talking with some philosophers of physics over the weekend. I was at a conference about philosophy of physics, which is a fascinating subject, which is a totally other conversation. But one of the things that we were talking about is like the difference between an observation that is impossible in principle or an observation that is just impossible based on current technology, and how those definitions change based on how our understanding of things change. So it may be that, dark matter could be impossible in principle to observe in the way that we want to observe it because it may just not interact with anything but gravity. Or it may be that, we just haven't found the way to observe it yet because we don't know its properties yet, and maybe it does weak nuclear interactions or something like that, right? One of the examples that this philosopher I was talking with brought up was like the stars. Like when it was first proposed that the stars were, made of the same kind of stuff as the sun, like it was impossible in principle to ever really know what they were made of because you could never go to a star and take a sample. And that was how you figured out what chemicals were in something, is you took a sample and you looked at the chemicals. And then spectroscopy was developed, and suddenly we can just look at the light and spread it out in a prism and look at the absorption lines or emission lines and know the chemical makeup of something a million,
like a gajillion miles away.
Yeah, like light years away, we can know what it's made of. And that's kind of wild that we're able to do that. And that's such an incredibly important tool in astronomy, is the fact that we know the chemistry of all these other stars. And
so maybe it's similar that, it's just that our current methods don't allow us to observe dark matter directly, but we'll have new methods or different methods maybe in the future.
Yeah, or maybe it has some particle interaction that we don't know about yet.
Yeah.
And, we just haven't looked in the right way to see that particle interaction. Like there's stuff like that could end up happening that'll turn out to make it so that we just didn't have the right technology to see this stuff yet.
Does this lead us to dark energy?
Yes. Yeah. So thank you for that Very helpful segue.
Okay, so there is time, but of course for us, the arrow of time points toward more entropy, more disorder. It points away from cosmic noon and toward cosmic dust. It points toward, for lack of a better term, death. Which is definitely a bummer, don't get me wrong, but humans have invented certain strategies for dealing with the inexorable arrow of time, including life insurance, which provides your family or other loved ones a safety net in the eventuality of your passing. In an unpredictable world where only death can reliably be predicted, you need life insurance. And with Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options are 100% online and let you avoid unnecessary medical exams, and Policy Genius helps you easily compare your options from America's top insurers with just a few clicks. Their award-winning agents can even walk you through the process step by step. So get peace of mind by finding the right life insurance with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. Policy Genius, because the arrow of time, at least as we experience it, only goes in one direction. Katie talked earlier about a key difference between cosmology and archaeology. Archaeologists build an image of the past based on information they can gather from a small amount of remains, but cosmologists are able to directly look at different times in the universe's history through the way light travels. They don't just use one piece to imagine the whole, they can actually witness the whole itself, and that allows us to learn a lot. Like, galactic archaeologists can map out the stars in our galaxy to help us determine how our solar system was formed, and astronomers can use spectroscopy to determine what distant stars are made of. These are discoveries early scientists could only dream of making, and as technology continues to advance, we may be able to learn even more about our universe.
Okay, so we've talked about the expansion of the universe, right? And then we talked about this balance between the gravity is pulling things together, expansion is pulling the universe apart. And I'm careful about the wording of that because the expansion of the universe is not like pulling galaxies apart. It's just making more space in between galaxies.
Right.
Things that are already gravitationally bound stay gravitationally bound.
Good.
So, yeah. So, dark energy is we're going to get into that. But the expansion of the universe is not pulling apart things that are gravitationally bound. There could be a caveat to that, which we'll get into much later, I think. But the way we understand the expansion of the universe is just making more space in between things that are already bound. So since we can look at the past of the universe, and since we can trace out how the expansion has been changing over time, from the first moment that we understood the universe was expanding, there was a question of, will it keep expanding forever? Or will it not, right? We know the universe has been expanding since the beginning. And we know that the universe was expanding faster in the earlier times than now, to some degree. That makes sense because, so imagine, the Big Bang kicked off the expansion of the universe. Don't know exactly how that happened, but let's say that kicked off the expansion of the universe. Everything's kind of moving away from everything else, but gravity is trying to pull everything back together, right? Because gravity always exists, and all these galaxies that are moving apart in the expansion of the universe, they still feel the gravity toward each other. And that kind of that should just slow the process down. Right, that should kind of put the brakes on this expansion process. So it should be kind of like a drag term or something, right? It should just slow things down. And it's been known for a long time that that's how this should happen. That the Big Bang was the thing that set it off, and then gravity should be slowing it down. And so there was this question, how is this going to balance out? Is the gravity going to be enough to eventually stop the expansion? and then everything will fall back together? Or was the expansion so powerful that, even though gravity is always slowing it down, it'll keep going? And it's kind of like if you take a ball and you throw it up into the air, like what happens to that ball is you give it an initial push, right, with your hand, and then as it's moving up from your hand, its gravity and the Earth's gravity are pulling together, right? And so that slows it down as it's moving upward. Eventually, it slows it enough that it stops and it falls back. If you were able to throw it in an inhumanly fast way, like if you could throw it at 11.2 kilometers a second, the escape velocity of the Earth, then what that means is that it would always be slowing down, but it would never stop and fall back. Right, so it would stop at infinity if you flew it at exactly that speed. If you threw it faster, it would keep going forever. It would be slowing down a little bit. If you threw it really fast, it would kind of get to a constant speed as it's really far away. But like it would be slowing down initially, at least as it's moving away, and then it'll never stop and fall back. But it'll kind of get to like a constant speed or it'll get to some infinite distance or whatever, right? And those are kind of like, those make sense as the possibilities for the universe, because we're still just talking about expansion and gravity. And so it's kind of very similar physics. Like the universe, there was the Big Bang, that's the initial push, and then there's the gravity of everything kind of trying to fall back. And it's just gravity. So there's no other forces that we're considering in this process. And so in the late 1990s, astronomers were doing measurements of the expansion history of the universe to try to figure out what that kind of curve looks like, to see if the expansion is slowing down so much that everything will come back and recollapse, or is the expansion just slowing down a little bit so that we're going to keep expanding forever.
And these have big implications for the long-term future of the universe, I assume, because in one way we crunch back together, and in another way we just keep getting further apart from everything else forever.
Right, exactly. And implications for like the overall kind of geometry of the universe in a way I think we talked about before, where you can have like a flat geometry or a curved geometry, which has to do with kind of like the large scale effect of gravity on the shape of space. And I don't want to get into that too much at the moment, but the measurement of the expansion history kind of gives you information about that, right? And the way you measure the expansion history is you look at least in the way they were doing it this time, so they look at distant supernovae at different redshifts. And there's a way we can kind of get the distance to supernovae. It's a complicated process that involves several steps. But if we can see a supernova and we see the brightness and we see the how the brightness rises and falls as the supernova progresses, that gives us an idea of the physical distance to that supernova in a particular way of measuring that physical distance.
So it's like a yardstick almost.
Yeah, exactly.
Okay.
Exactly. That tells us something about the sort of physical expansion and also the timing, because you also have the redshift. And so you can kind of put that together into a timeline of the expansion history of the universe. And so they were doing these measurements, and they were trying to measure a number called the deceleration parameter. It was written as Q0. And this deceleration parameter would tell you if it's too high, then it means we're going to recollapse. If it's a low number, we're not decelerating that much, we can keep expanding forever. And so they measured this, and they found that the deceleration parameter was a negative number.
What does that mean?
Which means that the expansion is not slowing down, it's speeding up.
Oh.
And so what they found was that as they were looking at the history of the expansion of the universe, it was slowing down for a while, but as of kind of recently, like, 6 billion years ago or so.
Super recent.
The expansion is speeding up.
Yeah.
Yeah.
Okay. So they found that this was a negative number, which meant the expansion was speeding up, which makes absolutely no sense in our metaphor of throwing the ball. It's like throwing the ball, and then there's a secret hand that keeps throwing the ball as it gets further away.
Exactly. Like a big wind comes and like throws it into the sky, or
like there's some cosmic wind that keeps pushing it faster and faster.
Yeah. And there was nothing included in our models that should have done that.
Is that what dark energy is?
That's what dark energy is.
Oh, God, that's so much clearer to me than anything I've ever read or heard about it. Okay.
Good, yes.
It's the secret cosmic wind that's making the universe expand faster. So, okay, after the Big Bang, there were two options for our universe. Gravity would overtake expansion, causing our and other galaxies to crunch together, or expansion would overtake gravity, and they would keep spreading apart forever. And it turns out the latter is true, though, as tends to be the case, it's a little more complicated than that. Using Redshift, cosmologists were able to determine the expansion history of the universe, and they found that the universe is expanding faster than our models would expect. An invisible hand is moving the ball that is our universe upward and upward, faster and faster, and we currently do not entirely know why.
It's whatever's making the universe expand faster. We do not know what it is. We have some ideas. I'll tell you about one of them now, but something is making the universe expand faster. It's not included in our normal models of just gravity and expansion and time, right? We call it dark energy. So the kind of standard assumption about dark energy, the simplest model, I guess, is called a cosmological constant. And that's not a new idea. That's a very old idea, but it was used in a very different way when it was first invented. It was invented by Einstein.
Which isn't that old. I mean, when you talk about very old and very new, you just said something that happened like 6 billion years ago happened very recently. And then you said that Einstein's ideas were very old. And this is all problematizing my relationship with time further, Dr. Mack. You're making me think that time is not objective in any way.
I'm so sorry.
All the way back 6 billion years ago when Albert Einstein lived, who died like after I was born.
Okay, look. I mean, the acceleration started at a redshift of less than 1. That has to be recent, right?
Kind of recent.
Right?
But I would argue that Einstein was even recenter.
Yes, okay, but...
All right, so what was Einstein's cosmological constant?
Okay, so Einstein's cosmological constant, so he wrote a term into his equations of relativity, of general relativity, his equations that talk about, like, the expansion of the universe. He wrote a term into that equation. The letter used for it is lambda, which comes up later in how we talk about it. What he was trying to do was to keep the universe from having already collapsed upon itself.
Oh.
So at the time, he did not know the universe was expanding. Nobody knew the universe was expanding when he was first writing this stuff down. We didn't know other galaxies were a thing. Like, there was a lot that was just not known. Like, there were these so-called spiral nebulae, which were, like, they could see other galaxies, but they didn't know they were other galaxies. They thought they were just, like, clouds of gas, maybe, in our own galaxy. And so we thought at the time that, like, you know, the stars that we see in our sky, those are the universe, right? And there are these little nebulae out there. But there was enough known that we knew that they were massive objects, right? They knew there were things with mass. And they were just sitting there in the sky. And so there was this question, like, why have they not all collapsed and, like, clumped together from the gravity? Like, they've been there for a long time. They're just hanging out. Everything should have already collapsed on itself because gravity always pulls. All it does is pull. And we should just be in a big clump. We shouldn't have these, like, distant things sitting out there in space. The argument makes more sense if you think about it in terms of galaxies today, but at the time they were talking about stars and nebulae. And so the idea was that Einstein had, he was like, well, we can put in this extra term, and this term just balances the gravity. It just creates, like, a little push. It gives every little bit of space a little bit of, like, pushing, like a little expansion in it. And that will balance out the gravity of all this stuff that's trying to fall in.
And we know we need this lambda because we look at the sky and we notice that things haven't fallen all together.
Exactly. And it was to keep the universe static because at the time, people thought the universe was just static, right? It was just stable. And so this term would keep the universe stable. It would balance out the gravity so that everything hasn't already collapsed on itself. A few years later, the expansion of the universe was discovered. It was shown that those galaxies were actually really far away and they were moving away from us. The farther away, the faster away they were moving away from us. And that's all consistent with just the universe is getting bigger. Everything is moving away from everything else as the universe is expanding. And that explains why everything hasn't fallen together because it's still moving away. Like, however it started, it's still moving away. And that's why it has momentum, basically. That's why hasn't collapsed.
The push.
Yeah, yeah. And so Einstein was like, oh, I guess that term was a bad idea. He takes it out of the equations and, fine, you don't need that term anymore. You erase the lambda, everything makes sense. You have a history of expansion of the universe, and everything is moving away because it's expanding, and it hasn't fallen back because it's expanding. Like, it all makes sense, right?
Yeah.
But then it turns out that it doesn't make sense now, because now the universe is accelerating and we don't understand that.
Right.
If you put that lambda back in,
everything gets fixed.
Then it fixes it. Yeah, it fixes it like really, really well. Like what the lambda term does is it gives every little bit of space a little bit of like pushing, a little bit of expansion kind of built into it. So you imagine you have like a cubic meter of space. It has a little bit of expansion just built in. And so every cubic meter has this little bit of expansion built in. The reason that the acceleration only really took over at Redshift around 1 or 2/3 or something is because before that, the gravity of everything really was slowing down the universe, because there was a lot of stuff close together. Like the galaxies were close enough together that their mutual gravity was strong enough that it could slow down the expansion of the universe. But then they got farther away. The gravity between them got weaker because they're farther away just from the normal expansion. Even though it was slowing down, it was still happening. So the galaxies are getting farther away. Their gravity is getting weaker. And then at some point, the gravity between galaxies is so weak and there's so much space in the middle that little pushing from all of those little blocks of space in between is enough to start actually speeding up the expansion. So when the universe is big enough, there's enough space. Now there's way more space, so there's way more acceleration kind of built in. There's way more of this cosmological constant because it's just based on the amount of space, not any stuff exactly. So now there's more space, there's more cosmological constant. The universe can accelerate and expand faster and faster.
Wow. And that is what dark energy is this lambda.
Probably.
This cosmological constant.
That's our best guess at the moment, that it's probably a cosmological constant. All the data fits that perfectly, as far as we could tell. I mean, there's some error bars, right? Our measurements are not perfect, but all of our measurements are consistent with the expansion being due to a cosmological constant, just something built into space. People think of it as a vacuum energy that just creates this accelerated expansion. Now, when I say people think of it as a vacuum energy, there is a concept of vacuum energy, of 0-point energy, as like there's just some amount of energy that's just always in the universe, and interactions between particles can like kind of draw on that vacuum energy in some funny way. And it's why there's always some kind of energy in the universe, even when you seem to have like a total vacuum. You get things like virtual particles and all kinds of weird quantum stuff can happen. Now, if you calculate how much energy should be in the vacuum based on like that quantum stuff, that weird quantum stuff that happens, you get a totally different number than the vacuum energy that we need if it's just the cosmological constant. Like if you want to call the cosmological constant just the vacuum energy, you're off by like, I don't know, it's like 80 to 120 orders of magnitude based on how you calculate it. Like,
and that's a lot even for cosmologists.
Yeah. Yeah.
That was a cosmology joke, Katie. I'm learning.
Yeah, thank you. I feel appropriately humbled and insulted. Yes, it's a lot even for a cosmologist who waves a hand at an order of magnitude or two, and so we don't know why the cosmological constant is the number it is. Like that lambda has a number associated with it, which is just like has to do with how the expansion is accelerating.
But we also don't know why the number that is the speed of light is the number that is the speed of light.
That's true. Yeah.
We don't know why any of these numbers are the numbers that they are.
Yeah.
They just are. I mean, when I asked you why the speed of light is the speed of light, you were like, well, it just is.
Right. Yeah.
So can't that be the case for this cosmological constant? It just is?
I mean, yeah, but that's a very unsatisfying. I mean, the problem is that
That's how I feel about the speed of light, man. I feel very dissatisfied with your answer.
Right. Well, yeah. I mean, part of the problem is that it is just a shockingly small number.
Okay.
Like, we don't like really small numbers. We like everything to be a number of order 1, and it's not.
Because a really small number is so close to 0 that it makes you nervous? Is that why?
It's called fine-tuning.
Okay.
Right? So the problem is, like, like it makes it feel like somebody had to set things up just perfectly to like just almost cancel out, but not quite.
Yeah.
Like that's...
And then you start to get worried that there might be a god or something.
I mean, some people do. Some people do like use these kinds of things to, to argue for the existence of a god. Like there are various things that you can look at in the universe and say, that looks like it could be fine tuning. That looks like it's just too close a coincidence to just randomly happen. And some people use that to talk about God. I don't do that, but like some people do. But like we want to be able to explain like all of the numbers that we come up with. Like we want to be able to have some explanation for like the structure of physics and also all the numbers that come into physics.
Because one, it's unsatisfying. Two, it, to me, reads like, well, we have to make this work and this is a way to make it work, especially in a field where you directly observe so much. You're able to directly observe so much. You're able to directly measure so much. And even light, you can really directly measure the constantness of its speed. And you can be really confident about that.
Yeah.
So it's not just that like fine-tuning is a problem from like a theological perspective or whatever. It's also a bit of a problem from a physicist perspective, right? Because who's fine-tuning?
So let me give you an example of fine-tuning where, I mean, this is a little bit obscure, but I think it gets to the point of the question. There's an issue, a really obscure little issue in the theory of the strong interactions called the strong CP problem. And it has to do with symmetries of the theory and things that we measure where it looks like there should be some big discrepancy and we don't see it. There's a number that we think we should measure that should be close to 1, and it's just as close to 0 as we can measure. We can't find any, it's like less than 10 to the minus 10 or something like that. It's clearly pretty much 0, but we can't find any reason in the theory for that number to be 0. There's a term that should be in the equation, and that term should have a number to it, and it shouldn't be 0. It should be some number. But when we measure it, it's got to be very, very close to 0. Just based on like the measurements tell us it has to be very close to 0. The structure of the theory could allow any number at all, as far as we can tell.
And so that's suspicious.
It's suspicious. And so there's been this effort over the years to explain away the strong CP problem. And one of the suggestions is that there's some field that existed in the early universe and it like had some potential. And so it like settled to the bottom of its potential, like a ball settling to the bottom of a hill. And at the bottom of that potential, it gives you this 0 number, but it didn't start at 0. It just like settled there through a dynamical process. And people like that better, even though it sounds more complicated, people like that better because it would give you a reason for that number to be small.
Right. It would give you a physical reason, like a reason within physics.
Yes, yeah. We prefer a mechanism to give us something to be 0 or a small number. We don't want it to just automatically be a small number. It's kind of like one analogy for this particular problem that I read once was like you have like a pool table in a rocking ship, and the pool table is always exactly flat, and you just don't know why, right? Like or something like that. Like there's something weird happening where it shouldn't be quite that perfectly balanced.
Like it's theoretically possible, it's just extremely suspicious.
Yeah, it's suspicious. Yeah, and so we feel suspicious about the cosmological constant too because it's this really small number. And we don't like really small numbers.
Okay.
And we would rather it be 0 or big. Like that's kind of how we feel about these things.
Right.
So there's a huge complicated effort to try to explain the reason for the number being what it is through some kind of dynamical process or through maybe an environmental process. This is one where it's like maybe it's different numbers in different parts of the universe and it just happens to be this number in this part of the universe. But if we went like super, super far away in some direction, it might be a bigger number or a smaller number. And like And then you can get into anthropic arguments, which is like, well, if it were really big, then all of the galaxies would have been too far away and we would never have had the formation of our galaxy. We'd never have the formation of a whole bunch of stars, and therefore it can't be too big. You can make arguments about like, well, the smaller it is, the more time you have to form galaxies. And so, you know, more of the universe will have the smaller values than the bigger values. And so maybe it just makes sense that we happen to be in a part of the universe that has a smaller value. Those are anthropic arguments. It's hard to make those arguments really coherent because you need some kind of argument for the probability of being in different parts of the space, but then also it's like, well, we only have one measurement, so what does it even mean to have different probabilities in different parts of the space, right? Like, can that really tell us anything? And that gets really complicated. And I've been involved in those arguments before, and it gets very complicated.
And anthropic in this context means that, like, it's biased by us?
Yeah, by the observer. Yeah. I mean,
okay.
You can make an anthropic argument for, like, why we live on the surface of a planet instead of the center of the sun, right? Like, if we lived in the center of the sun, we wouldn't be here to tell you that we lived there.
Right.
And so it makes sense that we live on the surface of a planet and not in empty space or in a star. You know, it's not that, like, any first principles thing says that we have to live where we do. It's just that if we live somewhere else, we wouldn't be able to tell you that. And so that's the anthropic argument, basically, that, like, it's weighted by the number of observers who exist to tell you that they're observing the thing.
Right. Wow.
So, you know, there are some things where there's clearly an anthropic argument. There's clearly an anthropic argument for us not living on the center of in the center of the sun. But is there an anthropic argument for dark energy? I don't know. Right. For a cosmological constant? I don't know.
You know what this has really done for me? It has radically reshaped my understanding of the E.E. Cummings poem, I Carry Your Heart With Me, I Carry It in My Heart. Have you ever heard this poem?
I don't know this poem, no.
It's a banger.
Okay.
I'm gonna read a little part of it to you,
yeah.
so that we can debate whether or not E. Cummings was making a joke.
Okay, go for it.
Here's the deepest secret nobody knows. Here's the root of the root and the bud of the bud and the sky of a tree called life, which grows higher than soul can hope or mind can hide. And this is the wonder that's keeping the stars apart. I carry your heart. I carry it in my heart. This was written in 1952, I think.
Okay. Yeah. Yeah.
This is the wonder that's keeping the stars apart. Could that have been a direct reference to dark energy?
I mean, it could have been a direct reference to the cosmological constant before we knew about dark energy.
But we didn't know about dark energy in 1952. We actually didn't know about the wonder that's keeping the stars apart.
No, I mean, Einstein had that idea and had written it down, but then he rejected it.
Oh.
So it could be because he rejected it because the universe wasn't static, right? So he erased the lambda term. But it could be that the lambda term got into the public consciousness in some way enough.
Yeah, because I've always thought that was sort of a rejection of cosmology. You know, and like the real wonder that's keeping the stars apart is love or whatever. But then when you were talking about dark energy, I was like, whoa, this is the wonder that's keeping the stars apart.
Yeah.
So maybe he just saw it coming. Maybe he actually should be credited with the stuff that happened in the 90s. Yeah.
Yeah, maybe.
Well, I'm glad I could bring a little bit of poetry to this astrophysics podcast.
So we end this episode about Cosmic Noon with an appreciation for galactic archaeology and a sense of wonder toward dark energy as a possible explanation for the acceleration of the universe's expansion, the rate of which is uncertain, as shown by the Hubble tension. My goodness, this episode had some great names for things. Hubble tension? Banger. There's something to be said for the way these big questions about our universe lead us to different conclusions, I think. Like, what Einstein thought would keep the universe stable, in fact, has kept it consistently unstable. The concept of fine-tuning can make people turn to theological explanations or physical ones. And what Dr. Mack may see as decidedly scientific, I can nonetheless find poetic. Next time, we'll discuss the astrophysics of life and how life on Earth is even possible. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, with music and mix by Joseph Tuna Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our associate script editor is Annie Fillenworth. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.